So now we have the combined, this is a combined control drawing of several aspects that have been shown so far. The first thing is we have this output linearizer, which deals with the fact that this valve is strongly nonlinear or equal percentage. So that handles the nonlinearity. In this particular example, we have no dead time. So we've got no dead time in the process. So we've set that as 0. And I've put the turn down to 3 to 1. And given the range of 5,000, that means below about 1,500 odd, or below about 2,000, we're starting to get some noise, turn down noise, which is shown here. And we're going to get some turn down bias. Our previous videos that I've put together, this turn down effect was not totally representative of what we normally see. So I have added that characteristic into this model. So now we can see what happens, which is what we would normally see realistically as we start turning down into this very non-linear region. Well, just not the non-linear region, but the actual region where the flow meter struggles to get a reasonable reading. Your Reynolds number through the orifice meter is not sufficient, or creates a lot of turbulence or noise or unreliability. So what I'm going to do is I'm going to drop the set point down a little bit further into the region where we know there's going to be problems. And here's the process history view. And what I have added now the actual flow transmitter, which is in this magenta line here is the actual flow, and this green line here is the measurement. And what we can start seeing over here is that the measurement, which is the green line, as we took the set point down, started becoming very erratic, started behaving erratically. Now I'm going to go back and show you what it looks like as we've carried on. And this is quite common to see this oscillation in the PV as the flow transmitter starts becoming unreliable at the turn down point. And again, in previous examples, I've shown that it's hunting. So the blue line, which is superimposed, that blue line there is the output to the control valve. So you can see the flow transmitter responds fairly well. It's totally correlated, and because it's on the same scaling, it's almost shown overlapping the output. But because of the valve time constant, there's a filter in there. So we'll let it run for a bit, and I'm going to drop the set point even further down to 500, and it's going to give you a very good idea of the hunting effect or the oscillation around the lower set point. Now again, like I said, the loop it's been detuned. If we take it down even further, it could potentially get even worse, but this is about where we're going to have problems. You can see the PV's jumping, and what often happens is it's going to be detuned, or the PV filter time constant will be played with a bit. This is really not ideal because we're trying to control something that's unreliable. So the question is, what options do we have based on all of the other bits and pieces or other tools that I've gone through, methods that I've gone through, that we can address this? And this is possible, and it's basically what we need to do is we need to first understand where is this low range turn down becoming an issue for control, and what do we do at that point? What is there a fallback? Can we fall back to an estimated value? And if we fall back to the estimated value, how do we make sure that when we transmitter becomes good again, or moves into a region where it's reliable, how do we ensure that the transition between the estimated value and the good field value is smooth on the upward direction and as well as on the downward direction? So, and that's the question we need to answer, is can we build an estimation for the flow at this low region to give us a smoother measurement at this turn down point? So what I'm showing you here is basically the first problem we have to deal with is, let's estimate the flow transmitter at turn down. And this is a problem that I've spoken through in previous videos, but what I want to show here is what will happen if this is the actual R, this is the actual R value of the valve. We'll get to the relevance of this just now. And let's assume we're doing a curve fitting exercise, and this is the actual guessed, this is the guessed R. Well, you know, we did know that the R is sitting at a value of 9, but we're guessing R. Now the trick is to calculate this column of R values for valve lift, which is fairly straightforward. And what I just want to show is the model mismatch. So the blue line is the model mismatch. So at low flow it seems okay. At intermediate flow it's probably going to be overestimating the flow, and as we get closer to full range of the transmitter, it's going to get closer to a more reliable reading. How's the R calculated? Well, it's very straightforward. Calculate it as R to the power of the valve lift as a fraction minus 1 times the valve lift. It's basically missing the CV and a DP part. It's just to extract that first part of the equation, just to get the R as a function of valve lift, and it's normalized to 100. It gets the relevance of this shortly. So that's how one would do it. So this is an X, Y plot, and that's the first point that we have to deal with, and this is the first problem one would have to resolve, is taking plant data and getting this response curve. So now we need to talk through the solution to the low flow inferential or low flow estimation. And in this control drawing, what I've built is a complex block. In different systems you can do it in different ways. This is an AI block, an analog input block, and what I have is the field PV, in other words the PV coming from the transmitter, and the signal to the valve. Now there are some other parameters here. So for model mismatch purposes I've assumed a CV value of 4900, and we'll get to that now. And the DP I've left as 1 because that's how we modeled. We haven't put DP into this equation. And that XY plot of the R value, we need to drill into this block a little bit to understand how it works, where it's configured. What you need to know is that there are some other settings here. There's minimum bias and maximum bias, I'll get to now. There's a minimum PV and enforced minimum PV. So if these two values are true, or if the enforced PV value is true and the field PV value is below 1000, then it's going to not rely on the PV measurement from the field. It will rely on the estimation. Similarly, if you want to enforce a minimum output, this is saying if the valve is less than 7%, and that is saying enforce it, it means that below 7% valve lift you will revert to the flow estimations. If we plot valve lift versus flow, we're going to have something like that, and this is the X and that's flow. So we know that there is at some X value there's unreliability. So we can define 2 points cutoff for X and a cutoff for the flow. And you can enforce either one of them in this block. I'm going to get to the details of that now. Drilling into this block, the first part I'm going to zoom in on this is the signal characterizer, and this is a normal XY piecewise linear transform block. Again, if I pull up the X values, this will look familiar. It's at every 5% from going from 0 to 100%. So in other words, I'm taking the valve. If you look at the connections, taking the valve, the signal to the valve, I'm passing it in as the X value. The output value now is what we expect as the R value, scaled from 0 to 100. And I'm slowly scrolling down here, and I will pull up the references, but these values come from the curve fitting exercise. So this block over here converts the valve lift to an R value. Then I have put an approximated actuator time in here, so we're taking the instantaneous value and we're filtering it, because in the real world you're not going to instantaneously move the valve to that point. So this is just modeling or approximating the valve characteristics. Then the main calculation is done inside here, inside this calculation block, which I'll get to now. And what you can see is it's the R value is coming in. So this is basically R. The CV value, which is a constant which we've entered at this point, I've put model mismatch, is there. So we have R and we have CV. And the DP we've left is 1, and that I'll get to. You can also link that to a DP over the valve if you wish to. The field PV is the measurement from the field, so this is the raw value that we're trying to have a backup reading for. And then we can specify minimum maximum biases that we're willing to apply. So it's a multiplicative bias. Go into the code. So inside the code, inside this block, I'm not going to go into too much detail, but in essence we are calculating the estimated flow at every single time interval and calculating a bias value. So firstly, there's some cleaning up values to make sure no bad values go through. So we are in this calculation, this section here ensures that the DP is always greater than 0. In other words, we don't get a square root problem, which we'll see down here. If you square root a negative value, this calc block will fail. And the minimum and maximum bias, this is to clamp the biases. So this is for the bias handling as specified. And then the PV, because you can get negative readings from the field, we don't want a negative reading to come in either. So this is what this block does. This is just to clean up. This is good programming practice. It's just to clean up input variables being used in a calculation. Then we estimate the flow, and this should look familiar. It's the CV times the valve characteristic, which is this, is the R to the power of x minus 1 times x times the square root of the dP over the valve. And we calculate the current bias, which is instantaneous current bias. We clamp the bias between the specified values and output the value that's estimated. Now, if you look very carefully, it will this particular calculation always outputs the estimated value, and I'm dividing by 100 because the CV value is from 0 to 100 and not from 0 to 1. So this is just for scaling reasons. So that is the estimation block. So these 3 blocks over here, this converts the valve lift to the R value. This approximates the valve characteristics, so we don't have an instantaneous value. and this does the estimation of the flow, the current value. Now out 1 is the flow estimation, and out 2 is the bias. You can see it's at this moment it's clipped to 0.5. Then there's some logic that's put inside here. The logic down here is just to determine if we're enforcing the minimum PV and the minimum output, and these are standard blocks. So this is a calculation block in this particular example. This block puts out a value equal to the input if that is true. This does some comparison logic, and this determines whether we need to switch over to the estimated flow. And this output here says false, that I'm not inferring it or I'm not estimating it, and that is the current PV that is either being estimated or from the field. This transfer function block here, so the bias is filtered. That's the other thing I want to point out. You don't take the raw bias, you must filter it. So I'm taking the bias, I'm filtering it, and this block here handles the smooth transfer between the field value and the estimated value. So this is just to handle the bias in calc. So the bias actually gets passed through this filter, and it's passed into a transfer block, and the bias then multiplies this is a multiplication block, takes the estimation, multiplies it by bias, gives the PV value. This is another transfer block which handles the transition from the field PV to the inferred PV, and we have a balance time of 10 seconds. These blocks are built into the Emerson system. It can be handled differently on different systems, but the point of these two blocks is to ensure the transition from at the point where we know there's unreliability in the readings is smooth, and that the biasing is always done in a smooth fashion. And that's what this block, in essence, this calculation is doing. So you'll notice as we're running, this value is going to toggle a bit because we're moving over the regions where the reading in the field is unreliable, because we specified a minimum PV of 1000, which we know is too low, because typically it's going to be below 1500. So that's this block. So moving into the estimation block, I've added some model mismatch already with the R value, and I've also added model mismatch with the CV value that we see here. We know it should be about 5000. I've specified a minimum bias of 0.5, a maximum bias of 1.5. You can change that. You can also put logic in there to pick up if there's going to be a problem. Now we know 1000 at the minimum PV is not realistic, so we need to change that value to something like 1500. And now you'll see it will always show true. Yeah, and what we're not really going to see at this moment is the impact it has, because it's not connected. It's just running behind the scenes at this moment in time. So you can see in the original control drawing, the transmitter is going out, and it is following the line, and it's going back into the PID block. Now what we need to do is replace this connection here with this estimation, which I'm going to do and demonstrate in the next video. Just to give you an idea in terms of the process history, you can still see it hunting around where it is at the moment. So going back to the original control drawing, I have replaced the feedback path with this block here. So that is the estimated block. I've just moved the set point up to 2000 from 500 where we were to stop the hunting and allow the block to initialize. In theory, I could have taken this output connection here directly and sent it to that valve connection there, and I could have taken the transmitter PV and sent and connected it to there, but there was no need to do that. If I use these internal references, which is fine, it achieves the same result. So in this particular example now, it is running, and I have done a couple of downloads. If we zoom out a little bit, scroll back a bit, you'll see that's where we were originally. It was hunting with the set point at this time. That's where we were previously. The set point was at 500, and the actual flow reading was from the transmitter was actually running about 1000, just above 1500. The green line here was the PV, and it was hunting from the transmitter. So we've done some downloads, we've connected the object correctly, set to current time, and now I want to drop the set point back to 500. And let's have a look to see if we have the same problem we had before. Now, as it lines out, I'm just going to select the green line now, which is the actual measurement, which originally at this point would have, once it transitioned through 1500, we would have had noise. You'll notice now that the actual measurement that's being used for the control is firstly clean. That's the first thing. And the second thing to note is that it pretty much tracks the actual field measurement. So we've now overcome this transition problem. So now we've overcome this transition problem. You can see that the estimated value, here's the estimated value, and if we compare it to the actual theoretical, or the actual value that you would have if you had perfect flow measurement, they're pretty much the same values. Now we're going to transition back. I'm going to move the set point from here back to 1500, which is at the transition point, and allow the controller to function. Let's go back to the process history. Again, smooth. It smooths the whole way up. Not what we had previously, would have been hunting at this point still. And we're still at a region where we are inferring the value. It shows it there. The field value has to go above 1500 before we have this value is going to start toggling. So what I want to try and demonstrate is what happens when we're at a point where you could get toggling between these. Let's take it slightly higher than 1550. Take it slightly higher. The field PV, unfortunately, at this time is still not showing value greater than 1500. I was looking at the wrong value for a second there. If we go back, the field PV is still, the transmitter is unreliable, so we need to still take the set point up even higher. Let's take it to 1700. We want this transmitter value has to go above 1500. Let's take it up to even 2000. There we go. Now this value is now starting to become reliable. And you'll see it switched over. At this point now, what you'll see is that we are not inferring, and that this value here is going to start going closer to the transmitter value. and at this point it now tracks the transmitter, and you should see the noise in the signal here, and there's the noise that's coming through. So through the entire range of where the reading was unreliable, this fallback mechanism worked perfectly, and because we have this output linearizer, the feedback response has the same rise time throughout the entire operating range. So this has basically solved several problems which one sees in industry: low flow turndown, fallback on an estimated value, and nonlinear flow to valve lift characteristics, which is resolved using this linearizer block and mechanism. So solved several problems fairly simply in one foul swoop. This particular way of addressing flow and turn down problems I've used successfully in multiple places on multiple final control systems, and it always works. Specifically during startup, it assists the operators. What I often do is bring in this false or true flag, and you show it to the panel operator to allow them to be aware of the fact that the reading that they're seeing that's being used by the PID block is not actually the field reading. You can show them the raw field reading, but it's an estimated reading. You can also expand into this block and get the bias. If we go inside here, you'll see the bias is being calculated here. If it starts being clipped to the maximum or minimum values, then you also know there's a problem. Something might have changed in the field. So it's a good diagnostic tool as well.